we were discussing some basic like operations like addition, multiplication, subtraction, and we said that if we do these operations, the number of levels or the intensity levels which are between 0 and 255, okay, it may vary. It may go from 0 to 512, sorry, 510. If it is addition or subtraction, it can vary. Okay. In any case, we have to do a normalization this way. Okay. So let's say I give you any image to do some operation, the values will change. So it is understood that you have to identify this equation. Okay, this is like a very fundamental thing that you have to do it. Even if in the numerical, if I don't do it, doesn't mean that it's not needed. You have to make sure that it's between 0 and 255 or 0 and any level that we have. Okay, this is what we did. We did some multiplication. We said multiplication is term by term multiplication in image. We did some quick examples, and also we saw that what's the application of the addition and subtraction. We can easily see that this helps in denoising. Okay, and we discussed in detail. This is the last lecture. Okay. Yes. Yes.
What do you mean denoising here?
Here, okay, so we give an example that why we want to act with two images or more than two images. Okay, so we give an example. Let's say you have a camera that's still camera, okay, and there's some noise, okay, in that camera, but the scene is itself is constant.
Okay.
Okay, so normally noise is what? Any distortion. It can be any, let's say, fog or smoke. Okay, let's say. So it is moving. It will not be still, but the scene itself is still. Okay, so if I take some pictures regularly, like after 1 second or 2 seconds, and I just stack them, so it will enhance the image. It will reduce that noise. Okay, so this is one of the just very simple application of denoising by just stacking or taking the mean.
Okay, there's another question regarding subtracting the function.
Yeah.
What's the method?
Yeah, subtraction is actually can be two ways. Either you are comparing two images, okay, just like an error, or you, let's say you have a reference image, and there's something like in biomedical, you have image of a healthy patient and some other with some disease, some maybe tumor or something. Find something good. Yes, anything that is interesting to doctor. Yes, before. Okay. So yeah, before and after treatment can be this. Okay, we did some quick example. If you are not there, try to run this example. This is doing the same thing. If you're good in MATLAB, we have this. If you're good in Python, we also have 3 examples. This is the reference image, okay, and a live image, and we just subtract these two to get this, and then we do some processing to basically to enhance the subtraction. But anyhow, we'll do this. Similarly, if you have a shade and we know that this is the division, we can take this, divide by this to get the clear image. Okay, so yeah, so division multiplication is very simple operation, but in image it's very, I will say, powerful. So what we are doing was a single pixel operation. You take a pixel, try to find according to some function, we try to modify the image itself. Okay, let's say we want to take the negative of that. Means that all the values from 0 to 255 be inverted. Okay, so how we can do is, this is just an inverse. So how you can do, you just subtract all the pixel from 255 to get this. Okay, what is the benefit again? It's mostly its benefit is either, and if you are, like, let's say in the phone you have what? You have like filter that creates the negative. This is one of the application. The other is the medical. Okay, so sometimes what is happening that the original image in medical is not clear, but if you take the negative, some of the things get very clear. And I have some example later on. I will show you this as well. Okay, here we call it contrast stretching. So basically, what we are doing, the pixels onto the lower side, which is the darker ones, are mapped towards the more darker. So darker gets darker, the lighter becomes lighter. This is the input, the image itself. These are the pixels of the image, and this is the output of that. So basically, we are stretching the contrast. Okay. Similarly, here we are just doing thresholding, like above K, I just make it high, and below low. Okay, so it's create a black and white, which is good for segmentation.
What do you mean?
Let's say you have a picture in which we have some objects. Okay, so I want to subtract. Okay, and here this is very basic example. So these are the examples. Okay, of this. You see contrast attachment, so it's improved or enhanced the image very well. If it is too dark or too light, it is straight. Then we said, okay, this was the single pixel. We take a pixel and we are doing something. The operation itself on the pixel does not depend on the neighbor's pixel. Okay, but however, we can have the neighbor operation of taking a small portion and taking the average of that. Okay, how it is done? Let's say you have a image 3 by 3. Okay, I can take the portion of 3 by 3 and add all of them and divide by the total number, and similarly move on. So I start with this one like this. Okay, the outside are zeros. Assume everything outside is 0. Okay, and we call it padding. There's several ways to do this, but the simple is to use the 0 pad. Okay, and we add all of them like 10 plus 50 plus 20 plus 100 divide by 9 is the average, and we assign this value to the middle one, which is 20 now, and then I slide it, okay, to 50, and whatever comes in the box I add, divide by 9, 42. Similarly like this, then the other row, then the other row, we get this. Okay, this is called the averaging or the mean filter. The last topic that we were discussing was the geometric mean. Like for example, here we are shifting the image or stretching or contracting or making something. We are changing the shape. Previously we were changing the pixel values. Now geometric means from the name, We are changing the shape, not the pixel itself. Okay. The general form of this is like this is the pixel, not the value, but the coordinate x and y. So we multiply with some matrix, and depending on that matrix, the behavior will be defined. How? You can see this. If I take that matrix identity, nothing will be changed. Everything is same. Okay, because it's identity. But if we just multiply with some number greater than 0, we'll get greater than 1. Sorry. So it will be enlarged. If we want to shift it, rotate it based on value of theta, let's say 90 degree will be shifted by like this. Okay, so it's like maybe 45 degree or less than 45 degree. If you put that, you will get this.
I asked last time I repeat my question. After the object, the size of the pixel is not changing, right? It's still same.
Size is not changing. The location will change, and definitely when the location will change. So let's say originally it was 1 and 1. So the 1 and 1 pixel, and let's say cx and cy is 2. Both are 2. Okay. So original x and y are 1 and 1. That 1 and 1 value of the pixel will be changed to 2 and 2. So what will be on in between? 1 and 1 will be what? You can either you can have zeros, but it will not be actually if you have put 0. So what you do? Interpolate, right? Yes, first you can put 0, but then you have to interpolate, and that is that we did before. Okay. So here again, it's a shift. It's not a shift. It's like making y same, but x is shifted. Okay. So based on the value of x, this will be like a kind of a stretching. We call it a shear, vertical shear, like the force. Okay. Similarly, here we are just the same picture. We are shifting any position, and this is horizontal shear, like a force that is forcing the picture like this. So this is very easy to understand nowadays because you have a lot of filters in your phone that do these things. So this is nothing. Let's say make your face like remove your double chin. So how to do that? It will just strategy of fixed rotation. For example, if I give you a matrix and I want to rotate it 90 degree, condition is we have this formula. Okay, so what we will do, we'll take the pixel x and y, whatever is the pixel. Okay, and since theta is 90 degree, so cos 90 will be 0. So x dash will be what? X dash will be minus y, right? And what about y dash? It will be x, right? If I shift to 90 degree, it will be like this. Okay. The other things that we want to study is the separability and the symmetry operation. Okay, so we talk about the mean filter. We take a block and we slide over it. The same operation can be performed in a row wise. Instead of a box, I take a vector like this and try to do this first and then row wise second. Okay, or in other words, since image is a matrix, I can reduce the number of operation by doing the vector wise operation instead of the matrix wise. So how I can do a vector wise operation? I can do row wise and then column wise. Okay, but this will only be happen when the operation itself is a separable. What do you mean by separable? If I take that function on the x-axis and on the y-axis, if I multiply them, I get the original function. If I have that function, I can separate them in a row and column operation. What is symmetric if both are equal? This is symmetric. What are the examples? Let's say an exponential. If that is exponential in x and y, I can write in product of these two, right? This is separable. So in this way, let's say I take an image and I want to do operation using this function. So instead of that, I can do first row wise and column wise separately. So this will be same, but this will be same operation. So multiplication and addition will be same. How much? We'll discuss this. Fine. Can you give me any numerical example? So let's say numerical, I want to multiply my image per model actually, but we'll discuss what is convolution. Okay, let's say this matrix can be formed by two vectors. Okay, so if I am doing some operation using this matrix on the image, instead of taking whole, I can take this first do column and then row. So this will be same. How to break the matrix into two vectors? One is the row and one column. This is I will tell you. You cannot break all the matrix. There's some properties that you have to follow, but that is future topic. We'll discuss it. Okay, let's go. Yeah, which one is symmetric? Yeah, this is symmetric because these two are equal. Okay, same. Top will be same if m and n are same. Okay, and v and u and x, y all are equal, then they are same. Okay, otherwise no. Okay, now there's another thing. We consider the pixels as these random variables because the pixel can take any value, right, between 0 and 255, ideally, or 0 to any value. Okay, there is a method which we'll discuss in the maybe next class that depends on these random variables, and that method is very, I like that method. It's like a kind of method. Okay, how, and this depends on this thing. Now, what is the probability of any pixel? Probability of the intensity of any pixel. Okay, let me start with very basic. You have this number of vector, let's say. Okay, simple. Let's say this. Okay, so what is the probability of 1 here? 1 by 5. Okay, if you have an image, what is the probability of 1? 2 is 4 by 9. Probability of any intensity value between 0 and 255 is what? The number of repetitions in the image divided by the total size of the image. This is the probability. Right? And if I sum that probability, I should get 1. Yes, it should be equal to 1. Probability of all the numbers should be equal to 1. What is the mean? How do we get mean of this?
Summation of the value times the itself probability.
Right? The value multiplied by the probability will give you the mean value of this, right?
Yeah.
What is the simple way to calculate mean? Add them and divide by total value.
If they all have the same rule.
Okay. So this is a statistic way of calculating the probability, right? Yes or no?
Yes.
Okay. Mean is the mean intensity level. Okay. What is the variance now? The variance is the spread of the other pixels around the mean. Okay. Okay. So this is the variance, right? Why I'm stress on this, because we will use this later on. Okay. So you just keep in mind. It's simple. If I ask you to find the probability, count the number of times that pixel is appearing, divide by the total. That's probability. So let's say if n is 0, what will be this expression equal to? Sum of the probability, which is 1. Okay. So we had 0, which is like n is 0. It should be 1. Yes. What about 2? 2 is variance, right? 2 which is variance. 1 it's 0. How can you prove that this is 0? Mean of what? If n is 1, I will multiply this term with this term, this term with this term. So if multiply with this will give you this term, which is m. Let me open it. Here, sum z of k, p of z k, which is m, minus m sum of p k, right? P z k. What is this? M minus n is 0. Yes or no? It's a general term that defines mean, variance, and some other moments. Our concern is this variance. How much is the spread of a pixel intensity? There's a method called histogram equalization. Based on this, the more is the uniform is the spread, the more good image will be. Okay, that we will discuss in the next class. Okay, so just wait for that. Okay. Okay, as I mentioned, either you can use the probability of as you said, we can also just sum of all the pixels, divide by this can be done, but sometimes that is easier than this one. But nevertheless, you can use this one. Okay, so this is the what mean shows you the mean of the intensity, which is the brightness, how bright and how dark image is. I can take the mean and say that this is the value, then it will give me a number. Fine. Now here, what is variance? Variance is the brightness spread, that how spread it is inside the image. Okay.
Sometimes take a mobile photo, it's like in the daytime. I need to focus.
Very good example. See, yeah. So let's say if you have sunlight at the one side, the pixel will be dark, some dark and some light. Right?
Yeah.
So what you can expect is there is some area which is away from the mean. I want every pixel near the mean. If I do this with the same image, you will see that the energy is spread and image will become very uniform. And this is what we will do for histogram equalization method. That we will do it next. Okay. Now, how to enhance that? One of the methods that we discussed was the point-wise operation. We did this, but we again will see it in this set of slides. Okay. So in slides, we'll focus our method on the point-wise intensity transformation, where I will take a pixel and do some operation, regardless what is outside that pixel. Like the neighbors, I'm not considering it. Okay. Is this clear? So what do we mean by image enhancement? So that image enhancement is actually we will try to enhance image, or we try to process image such that the result will be more suitable than the original image. Suitability depends on the application and the way we look at it. Sometimes we are very happy, we want to see our face like more bright. Okay, sometimes no, it's apology and just a dark background maybe. Okay, so it depends on the situation. Sometimes making the image more dark, let's say in medical application, make the thing easy. Sometimes making more light, make it easy. So there's no relative term, not quantitative term like the signals we have. Images are always relative. Okay, to the field and to the application, to the suitability of the time, whatever. Okay, a method which is quite useful for enhancing an image may not necessarily be the best approach for enhancing another image. Okay, so therefore we have to have series of methods. Okay, or the bunch of methods that we can pick here and there, try to find our best. Okay, so common reason for enhancement includes improving visual quality, improving recognition accuracy. I think this is very basic. Okay, so now one way is either to stay in the spatial domain or transform to frequency domain. Frequency domain is the next topic, so we'll discuss the spatial domain. Even in the spatial domain, we have two methods. One is the point-wise, in which we just take pixel do operation, and the other is the neighborhood, in which we take the neighbor pixels as well. Okay, so the neighborhood method is called the filter or the mask operation, which is again the next topic. We will be here in the point operation. So we have now three methods. In these three methods, if I consider the point or the filter operation, the spatial domain, I can have three types of transformation. One is again, which I explained to you, which is the point operation, which we did it. This is the thresholding. This is the stretching. Okay, so we take a pixel, try to find some mapping from input to output. This is the first method. The second is to take some, not only that pixel, but the neighbor pixels. Okay, this is the second, which we call it the local intensity method. Okay, we call it the spatial filtering that we try to apply on the image. The third method, we call it the global intensity transformation, in which we take the whole image to process it. And histogram equalization comes into that one. Okay, or the neural networks also, the CNN, because they take the whole image and try to find some information. Okay, so basically we have three methods. One is just pixel wise, That is local, it takes some pixel, but just the local inside the image, and the other is taking the whole. Okay, so yes.
Victor, you say pixel. I don't know what's the importance for that. I can't see if we have the whole the picture is nice, but I get the portion for it. I need to.
No, it's not like this. It's a different type of method for this. You say I can apply all three for the same problem, okay, but one may perform better than the other. It's not like this. Let's say if I want to, if the image is too dark and I want to make it light, I can do it by pixel operation. I can do it by
pixel operation. You go individual pixel.
The ones we did. Okay. Yes. And the second is either I take the filter or the portion, okay, or I can do
segmentation.
Segmentation and work on it. The third is to take the whole image. So I can do the same thing for this, but every method has an advantage, disadvantage. Some methods apply to specific applications. Okay. So the basic intensity method that we already discussed. One of them is the thresholding. If I just we discuss the thresholding, right? So you take a value, let's say some threshold above that 1, below this 0. Okay. Other point operation can be, let's say I add each pixel by 20 numbers, okay, so which means I'm increasing the intensity, right? Okay, so it's like becoming more bright. So this is dark, this become more bright. And if I just try to do x minus y, it's basically I'm flipping it. Yes, okay. So now what I want to brighten it up, okay? At the same time, I want these edges to be highlighted. Okay, in order to make sure that, so how to do that, there is what we call it sharpening filter. So we can apply a sharpening filter here, okay? Okay, so now what point operation can do, if the pixel is too dark, we can make it lighter, and if a pixel is too light, we can make it dark. Okay, how we can do, we will see now. Previously, we discussed just point operation like the negative, contrast stretching, and thresholding, but there are more than that. Okay, this is negative, right? Okay, then we can have this one as well. What log function, and then anti-log, and we can also have the power nth root, and we can have the nth power, which will give me the opposite to that. Changing the root, similarly changing the power, I can shift the curve more straight or more curved. So now see this curve, if I'm here, which is nth root, okay, if I'm here, what I'm doing, making it darker, making it brighter. Why? Okay, if I am here, what I am doing, making it darker, making it brighter. Okay, let's see this. So based on all these curves, we can either have a linear, which is negative, and definitely identity, which will not make anything, so it's okay. So either we have a negative, either we have a log, and similarly we have inverse log, okay, and this will do the opposite function. One will make it dark, one will make it light, okay. Then you have a power log, like power law is nth root, okay, or nth root or nth power. So we call collectively all of them as power law, okay. And then you have piecewise linear. We will discuss this after that, okay. So how to do, let's say I have any of this curve, how to do in a computer. So in a computer, I will have a lookup table that will map one point to another point. This is just for a computer, nothing else. Like 64 will be mapped to 32, this will be mapped to this will be like this, okay. So anyhow, this is just out of the scope of this. Anyhow, this again, negative is L minus 1 minus R. What is L? L is number of the levels. Let's say 256 in an image. So it will be 255 minus intensity level. And as I mentioned, that sometime visibility. Okay, similarly here you see there's something here and it's also here. Definitely a doctor can tell that which one is better. Okay, so this is just an example, you can do it. Okay, now what is, there was identity, then there was log. Okay, so log will give you something like this. Okay, so it means that the darker pixels I'm mapping towards the lighter one. So it means that I'm extending it. However, the lighter ones are still towards the lighter point. Right. So what I'm doing, if I apply this on an image, it will make it brighter. Okay, now the exact application of this is in Fourier domain. Let's say this is a Fourier transform of any image. How it is calculated, we'll see later. But now this is a Fourier transform of the image, which has some points which are not visible. Okay, so if I apply this, you can see some points, some components of the frequency domain are becoming visible. Now, if I convert it back to the time domain or the spatial domain, I will get some of these features more visible. Okay, so let's see. I want to apply this log transformation. Okay, so this log transformation, this is the image, and let's say this is the either constant or this. So what I will do is very simple. I take these values and put it into this. The new values will be S, right? So first case, I take C is equal to 1 and I start putting all these values here. Okay, try to calculate what will be S once it's been there. So this is my new image. Okay, so it's simple. Just put the value expression. You have the expression, put the value. Either now see, either you can have a lookup table, but the lookup table is for the computers. For us, I should have the expression to calculate it. Fine. Similarly, if C is not a constant, but it again is a log 10, 1 plus L. So what is this? The total intensity levels, which is 128 total level, right? Because of the quantization. Then I can just directly apply this log here, and to get the numbers round off, definitely we have to round off.
Right? So why all?
Because it's 2.
So all the matrix is equal to 2?
2, yes.
All the matrix?
Yeah.
So all the bits?
Yeah, for this example, yes, 2.
I mean for this one,
right? Yes, for this it will all be 2.
All would be 2, and this is another example.
Yeah, this example is the second part where we take the C equals to this, and here you can see that it's not 2 but 3. Okay. Okay, let's discuss the power law transformation between the next class.